Welcome back to The Explainer. Let's just jump straight into it, because today we're exploring the absolutely fascinating world of proactive breaker health. I want you to imagine treating your electrical switchgear kind of like a patient in a hospital, hooked up to an array of highly sensitive monitors. We're going to look at the exact traces and vital signs that tell us a machine is getting sick long before it actually codes.
So why wait for a circuit breaker to fail? It's a simple question. But what's really interesting here is that a circuit breaker doesn't actually just fail out of nowhere without warning. It degrades gradually, and every single step of that degradation leaves measurable traces along the way. We just need to know how to listen to what the breaker is telling us.
If you recall our previous discussions, we looked at reactive safety nets, like breaker failure protection. Now that's your safety net, isolating faults after a primary breaker has already failed to do its job. But today, we're completely shifting our mindset. We are moving from reactive nets to proactive health tracking. The entire goal here is to catch that mechanical degradation incredibly early, effectively preventing a catastrophic failure scenario from ever happening in the first place.
Looking at this breaker mechanism cutaway, you can really see the physical reality of what we're dealing with. A breaker's rated mechanical life might be specified for a strict 10,000 operations, or a maximum number of fault interruptions at its rated current. You've got heavy springs, linkages, moving contacts, energy storage mechanisms, the whole shebang. And every single time this thing operates, it undergoes mechanical wear and tear. Over months and years, friction goes up, lubricants dry out, parts wear down. But the absolute beauty of modern digital relays is that all of this mechanical wear can be continuously monitored electronically.
Section 1. Reading the vital signs. Let's move to our checkup panel and see how the Circuit Breaker Condition Monitoring Function, or SSBR, tracks a breaker's vital signs.
So notice how these 4 key performance indicators work together. Think of them kind of like a car's dashboard gauges. You've got your engine temperature, your oil pressure, your battery voltage. Well, no single gauge tells you the entire story of the car's health, but watching all of them together reveals subtle, underlying problems long before you find yourself broken down on the side of the highway. By tracking spring charging time, SF6 gas pressure, travel time, and inactivity time, we get a complete, real-time picture of its mechanical health.
Now, a really crucial point here regarding that second metric, SF6 gas pressure. It is incredibly important that you do not treat this as just another optional maintenance metric. Insufficient SF6 gas directly compromises the breaker's physical ability to safely quench an electrical arc during an interruption. If that gas is low, you don't just have a maintenance issue. You have a massive, safety-critical hazard on your hands.
And then we have inactivity time. What people often miss here is the paradox of nothing happening. We intuitively feel that if a breaker is just sitting there doing nothing, it's safe, it's in a stable state. But prolonged idleness is itself a severe degradation risk. Over time, those mechanical lubricants can dry out, and the complex mechanisms can literally stick together from disuse. If you aren't monitoring inactivity, you might command a breaker to trip after 2 years of silence, only to find it's completely seized up. No way do you want that.
So, keeping those vital signs in mind, let's do a quick reality check. When tracking these specific metrics in a facility, there is one major, fundamental mistake almost everyone makes. Think about how typical maintenance alerts are handled. What do you think that mistake is?
The answer? They wait for a KPI to cross a hard alarm threshold before taking any action. Notice the gradual 15% increase in charging time over 6 months right here. If you just wait for the alarm bell to ring, you miss the entire story playing out right in front of you. The much smarter, far more proactive approach is trending the data over time. If you see a spring charging time slowly creeping up, like that 15% increase over 6 months, that is a glaring maintenance signal. It tells you the energy storage mechanism is degrading right now, giving you the chance to fix it long before it crosses a hard limit and delays a critical trip.
Section 2. The unseen link. Trip circuit continuous supervision. Because mechanical health is really just one layer of this assurance. A mechanically perfect breaker is functionally useless if the control wire telling it to trip is broken. This brilliantly illustrates why the trip circuit supervision function, or TCSSCBR, is so vital. Think about it. A protection relay that is perfectly healthy is absolutely useless if the copper wire connecting it to the breaker's trip coil is compromised. TCSSCBR continuously monitors the integrity of that trip coil circuit, and crucially, it does this in both the breaker open and breaker closed states. Because the circuit topology changes depending on the breaker's position, this dual-state monitoring ensures there are zero blind spots. The RET615 relay doesn't just trust that the external wiring is okay because, well, it worked during last year's test. Instead, the TCSSCBR function runs a continuous, tiny test signal through the trip wiring at all times. It acts exactly like that little green power light on your smoke detector. It continuously confirms its readiness, so you are never surprised by a dead system at the exact moment a fire breaks out.
This is why this function matters so much. A wire can break, a terminal can loosen, or control voltage can just drop out on any random Tuesday afternoon between your scheduled yearly maintenance tests. Without this continuous supervision, you wouldn't know about the broken wire until a fault happens and the breaker fails to clear it. Therefore, any trip circuit supervision alarm should always be treated as absolutely urgent and investigated immediately. It literally means your primary defense is currently offline.
Section 3. Smarter Maintenance, Runtime versus Calendar. Okay, let's take a step back and look at the bigger picture to see how we apply this continuous monitoring mindset to the broader power system using the MDS-OPT function.
For decades, the industry has relied on calendar-based maintenance. You service a machine every 6 months, regardless of how much it was actually used. It's exactly like relying on a fixed date on a sticker in your car window for an oil change, rather than checking your actual odometer. By utilizing actual runtime data instead, we prevent wasted maintenance then on equipment that just sat idle, and we prevent unplanned failures on equipment that's been working overtime.
To put that into perspective, consider the numbers 5 to 10. This is the multiplier difference in operating hours you could easily see in a single year between two completely identical motors in the exact same plant. One motor is running a baseload continuously, and the other is only kicking on during peak demand. A rigid calendar-based schedule would service both of them at the exact same time, which completely ignores the reality of their mechanical wear. Runtime-based maintenance is about letting the data, not the calendar, dictate your actions.
So, as we wrap up this explainer, I want to leave you with this final critical thought. Think about your own facility. If your breaker's vital signs are gradually drifting and degrading right now, at this very moment, would your current maintenance program catch it before a fault does? Or are you just sitting there waiting for the alarm bells to ring? It's the difference between controlling your equipment and letting your equipment control you.